So, hi again. Great. So my name is Rachade, and I'm going to present you today a talk about artificial intelligence and personal medicine. If you have any question, please ask. I know I'll talk fast, so don't hesitate. And si vous avez des questions en français, je les prends pareil. So a little bit about me. I have a background in bioinformatics. I studied bioinformatics. I did my bachelor at the University of Montreal and my master's degree in Geneva. I work with pharma, biotech, and at the university. Different topic, still it's always the same point, it's biological data. People always try to figure out what I'm really doing. So I code, that's the tech obvious part, with biological data. So it's usually scripting, but it can be really more than that. So obviously all my work is to cure disease, to save more lives. After working for several biotech, since 6 months ago, I founded a startup. The goal is to help you personalize your nutrition according to your genetics. So it's still analyzing biological data, mostly genetics. And this comes from working in this domain and seeing that science is really evolving and there is so many things that we can apply in our health, of course. But between what is done in science and what people get, it's really not obvious. So really the goal is to make all this information easier. So artificial intelligence. So the goal of this talk is, of course, to make you more smarter. So to explain you more things. So what is intelligence? The word comes from Latin, that means understanding. And more you understand, more of course you can apply what you learn to different areas in your life. So basically, understanding more about genetics will help you understand more about how disease works and try to find a treatment for them. The other part of intelligence is really to compare computer to human. So I don't know if you have any idea about where humans are better than computer, because of course there are many areas. Any guess? Of course, every feeling, creativity, yes? Yes. Which kind of analysis? Yeah. That's totally true, and it depends on the area. So there is some place like to understand languages, it's really, really hard for computers to understand the meaning, not only the words. You have images also to see, to understand what you're seeing also. So even if we are trying to teach them how they should think, it's not always obvious. So the question about is the machine can think, it's really, as you said, the computer only knows what we teach it. So it cannot be better than us. It can do stuff faster, maybe more complicated, but never really better. I choose some historical facts, really not objective. I don't know if some of you heard about the Turk. It was the automation chess player. And it was been running over, I think, 80 years. And it was really great because you could play against machine. But it was a scam. There was real people inside it. who was playing chess. So it was a good start. In writing, we start to had artificial life with Frankenstein, attempt to create artificial life. There is also Rama's Universal Robot. That was a Czech play, and it was the first time the word robot was used in the English language. By the way, robot, I think in Czech means labor in the meaning of slavery labor, not work. Give you a little perspective. After the Second War, it started to be a little bit more interesting. So ENIAC was the first electronic computer that was really equivalent to electronical brain. Always the goal was to try to make computer think like us. Turing test, I think maybe you will be more familiar with this. It was the first time that we tried to measure machine intelligence. So the principle was really easy in theory. It's to compare human to machine with given a different set of query and with an imitation game, see if the computer had the same results. In 1956, this conference was the first time that artificial intelligence was defined as a science by itself and a specific area of research. So now you have more aspects when you can find artificial intelligence that maybe you are aware of. I don't know if you know this one. It was with Jeopardy. It was the first time that machine using advanced method was able to beat a man with a game. One of the interesting one. And this one, it's a cool one because it shows you that even with a lot of work and a lot of knowledge, it's still, technology can be disastrous. So it was a chatbot. Principle was really easy to talk to people and to understand what they are doing from what they are saying. And you have obvious stupid thing happens here. It was worse than this, by the way. I think in 24 hours, the bot was saying that Hitler was the better man around or something like this. So keep things in perspective. And tomorrow it really depends on what we are going to do with this kind of technology. So this is maybe the most complicated slide, but you have everything on it. So artificial intelligence is really a lot of things. So, and you can see the difference area that you may be aware of. So all the image perception, it's really different than robotic, than machine learning, than speech. But everything you see in intelligence artificial is somewhere, should be somewhere here. Personalized medicine. Switching subject because it's related, but give you some background. I don't know if some of you are aware, but what is it? Yes? No? Okay, cool. So I have slides for this. So basically, until now, it was when we develop a drug, we try to find one size that fits everyone. We take a little group of people, we try drugs on them, and if no one's died, it's working, and we sell it, and everyone doesn't respond the same way. Some of them help most of people, but it's not always the same way. And usually this kind of decision is based on disease subtype, risk profile, demography, and sometimes biomarkers. So now we are trying to do something more personalized with individual patient at the individual patient level. The big difference is now we start with the patient. We took all the omics data, genetics, proteomics, name it, preferences, health, history. We're starting to have a lot of data that even a doctor is not able to analyze himself. There is too many data. So we use a computer for this, but it's really more efficient. There is, for example, some treatment for cancer that you need to do a genetic test before, because if you don't have specific variation, it's not working on you. So the good thing is that if you have it, you are sure it will be working on you. So it's really the main goal of having some precision medicine. It's to develop different drug, different treatment for each of us. And to be more sure that it will work. Why personal medicine now? It's really because we want to customize healthcare. Decision for individual need to be really specific to the patient. Why we need it now? Because we see that there is a lot of treatment for the same disease, for example, and so you need to choose one. And usually there is one better than the other for the same person. It's also, there is a lot of heterogeneity over the population. So for two different people, the same treatment could not work. And for the same person, over time, it could not work the same way. So if for cancer, for example, if you are stage 1 or 2, it's not the same. It's not the same treatment, even if it's the same disease. And if your age is different, you have other criteria that could be based on. So how do we apply it? We try to tailor the treatment based on different characteristics of the people, so biological data and personal data. And we need it now because you have some diseases that are single-based, so you have a treatment A or B. And more and more we realize that more of the disease has really multiple steps. That means you need different treatment in different times, depending on where you are at the disease, which step. And the really goal of all of this is to deliver the right drug at the right dose at the right time. So it's really easy as a concept. It's really to do the best for you. So I come back to my super slide, and just for personal medicine, the area it's deep learning. It's under machine learning. So my talk will only be on this kind of example. You can have, for example, all the image recognition for radiology. We are using this. You can have other area in the healthcare that use other section of the artificial intelligence, but my talk will be really on deep learning, my example. Are you familiar with deep learning? No. Familiar with deep learning? A little bit, depend on, okay. So maybe it's too obvious, but I started from something easy. Try to start from something easy. You know Yoshua Bengio, I suppose? No? Okay, so it's easy. I'm going to quote him. It's going to be a good start. So he said that new revolution seems to be in the work after the Industrial Revolution, and deep learning is at the epicenter of it. So it's really important to understand how it works, and especially for personal medicine. So basically, that's how prediction was working. You start with DNA sequence, and you predict your risk. The problem with this kind of things is that it's not that simple. Phenotype is really complicated, and even if it's doesn't explain how it works. So you know that with some variation you have something, but how it works. And in biology, it's really important to know the mechanism, because if you want to do something about a disease, you need to know why it's happened, but how it works to try to change it. So deep learning, it's really just adding layers in this mechanism. So here, for example, you have the cell variable layer. So for the Mechanism itself, it's really easier, because if it's something happen in a cell variable, you can target this component, and it's simplify also the learning of your algo. This is just another example to show that it's still an artificial network, neural network. So you have a hidden layer, but you can have many layers, and you have data input. You still have output. It's still the same, but each neuron have different weight regarding of its importance, and with different several mathematical calcul, you can calculate the percentage of output, the probability. The hidden layer, for example, when you do this for cancer, can be one node, but it will be several clinical parameters, for example. Problem solving. So I have some examples. Startups examples. You have many startups that use deep learning for personal medicine. That means lots of things and nothing at the same time. So atom-wise, it's specific, and recursion, it's more for treatment disorder. Color, it's calculate the risk for you to have a certain type of cancer. All of those startup works with genomic data. Grace works on detected cancer. iCarbonics, it's more health management system. Social genetic is maybe the more famous one. It's in Switzerland, and they have a lot of data, so they can do better work. And they have good algorithm also to diagnostic and treat patients. Numerate, it's more for the drug design, so it's more for the chemistry. Whole biome, it's also for treatment disease, but it's based on not only on genetic data, but it's more also metabolic pathways and other biological information. And verily, I don't know if you heard about the All of Us program. It's a US program that tried to hire 1 million person and have them genetic tested to try to find to prevent and treat diseases. And there is this one. This one is from Toronto. They do deep learning for genetics. I think it's really simple, easy in their name, but they really make tools to use with genomic while doing deep learning. And the one I'm going to talk about, it's DeepBind. Any question until now? No? Really clear, everything? Okay. So DeepBind analyze how protein bind to DNA and RNA, and try to, so you have the DNA, try to see if the protein will bind to the target. So if you have DNA, RNA, is simple, no, not really, is it? Just something really maybe too simple. So you have the DNA, that's your genetic, and you have protein, and in between you have RNA. And protein can attach here or here, depending where. So it's really try to see if protein will bind to the right set, and if not, that can be a cause of disease. So what the tool does, it's basically still simple. They calibrate with over 30 parameters. This is done automatically, so they put data and have a threshold that determine if the information is correct or not. And after they train candidate, and finally they test the model. So the one of you who are aware of the machine learning system, so you always, of course, train when you have a set of data, you train your data on a subset, and it's not the one that you use your data on. I'm not sure if I'm clear, but basically this training data will not be in this part. It's only used to train the algorithm to understand what it's doing. So the goal is to give the algorithm data and to let him understand what is it in this case. Is it binding to is the protein binding or not? Yes. This, yeah, this tool, yeah, this is what it does. Because if it doesn't bind, that's mean, like for a disease you have a specific mechanism. So if something is not going, it's wrong. That's mean that can imply you have a disease. So specifically in this one, in this example, this is a binding site. So you have here a mutation from G, it's a T, and so the protein who should bind here, it's not binding. So if you have this mutation, that means you have a disease. Everything is genetic, so it depends on how you. So yeah, so that's the idea. The idea it's still only from this information you can predict that this person is more subject to be sick, to have this kind of disease. Only looking to the sequence. That's the goal here. Yes? You have two things. You have the DNA and you have the protein. So sometimes, so for here, for example, it's something here, it's not working. So you can fix it. Sometimes you cannot fix it. So if you have cancer, you have always probability because you have, this is like, this is specific to your DNA. You have something and it's automatically saying that you have a disease. Sometimes something from outside will interact here and you'll have a disease. That's what's happened with cancer. You still have some probability to have, your genetics will be different, but specifically is this. And your question about if it's genetic, you have some disease that you are born with it. So this is really, you cannot do anything about your genetic, but you have a lot of work, lot of disease that you can you can do something about this. So even this part of the helping, this is really this is the core of about precision medicine. It's really to try to understand what is wrong and how we can work on it. And this one is really easy example because it's only so binding site. If you have mutation and we know binding site, that means that on the biological mechanism we know where is it and what is doing. So we can target it and work on it and try to fix it. Sometimes we know you have, we just like we can have a population and look to the data and see that you have certain population that have a disease with kind of genetics, but you don't know how it's working, you don't know why. This is, there's a lot of disease like this. What maybe I should have mentioned. This, to use this, it's one line of code. So you only need your data. What they did, and why I'm presenting it, because they did all the algorithm, all the complicated stuff. So it depends on what you are trying to do. There's a lot of tools out there that could be used. I didn't talk about, I have no code on my presentation specifically because it depends on what you're working on and the kind of data you have and your preferences. I learned Java at my university. my first job, I was working with Perl because I don't have had any chance to use something else. And now I'm working with Python. There's lots of things with Python and R. So there's lots of people who try to do lots of algorithms. You have a team at the IRIC who also try to build new tools. But the specificity of this one is the only one for now that I know of, specific to deep learning in genomics. So you can just use it. You can, of course, try to understand it more, but it's really one, the way it's working is specific to genetic data. Yes? It depends on the kind of data you have and how much you have. But this kind of tools, when it's deep learning, it's machine learning. So you need to have lots of data because you need first to train your tool in it first. You cannot do it with one. This is for prediction. So if you wanna this kind of tool show you this kind of information, if you already have this kind of information, if you know that in this position, when you have this mutation here, that leads to a disease, this you can test it on one genome. And you have tool for this also. But this is to predict when you are working on a disease and try to look for a diagnostic or treatment. This is the kind of tool you can use. Question now? The deep learning thing, why it's good for genomic data, it's really because it adds layers. And the biology, it's really this. You don't have just DNA and protein, you have so many things in between. So it's really easier to make the process and to try to find target, because if you have different layers, you know, when you calculate everything and you have a probability, you know where the problem can come from, and you can test it in the lab because you still need to come back in the lab. So that's why it's the kind of data that's really interesting for deep learning. So, in summary, basically the personal medicine is really to help prevention, diagnostic, treatment, and patient engagement. That means almost everything. It's really using your own data to try to help you more. So it depends on the disease, if it's genetic or not, but you have, now we have the tools to capture all this information. As I said, the deep learning is really interesting for this kind of data, as we have now a lot of genetic data, and we have the tools to analyze them. We have the computer system. We start to have nice algorithm to analyze this, to process this specific data, and it's easier to understand after that how it works. It's still not really simple because disease is really complicated. It's not always, it's not binary. It's really percentage of. So you have more chance to develop a disease or not, and you can do some things to prevent it or not. And even the algorithm needs to be really flexible, as for genetics, the population is not the same. So you can train your data and have a prediction for a Caucasian population, and it's really working, and it's not for Afro-American population. And but we can capture it and we can work on it now. When you test when you do clinical research for a drug, this kind of data is not really captured. It also the algorithm needs to be flexible in time, because if we discover something, it needs to take more variable if we need it. So it's really, when you build something, you still need to work on it and to adapt. It's still, the tool still can do prediction, can be really accurate. We can still verify that if the algorithm says something, the percentage to be right is good, but we still need to understand how it works. And this is the big difference with genetics. It's not only that you are sure that you know your reason, but you really need to understand why is it to try to do something about it. For the data, we start to have a lot of data, but we need more. We need better quality, and we need to have the same kind of data. You can have different measures, you can have different parameters that are captured with different way. You can have your insulin taken, and you can have your genomic data, and you have a lot of tools that capture data, but just trying to merge them by themselves, it's really challenging. And the last issue is really about the ethical and confidentiality and social impact. So in Canada, there is no law yet. So it's not really easy to know where it's going. Maybe I assume that it will be the same thing that in US. In US, you have specific regulation for genetic data. So if you have, they cannot be used against you if you are looking for a job or for insurance company, for example. But you also have the ethical and social impact. Like if you do analysis and you know that you have, I don't know, 70% to develop a disease, do you want to know this kind of information? Do you know what it means? It's still a percentage. Sometimes you can do something about it, sometimes no. So it's really something people need to think about. And the legal issue. For now, there's a lot of places that you can have your gene tested. You can give your data to science research, but it's still up to you. And I'm done. Thank you.